So what the code is doing is reproducing the function f in form of a Fourier transform, right? So this is a two-step process. First, we are finding coefficients, and second, we are performing summation with these coefficients and reproducing the function. So here is my plan. I will run the code once, not close, clear, so that you will be attracted in order. Where is your? Oh, okay. You
Yeah, before and after.
Okay, so it's Spanish style.
Pretty much.
Don Gausado. So what I would do on your place, I would download, insert in directory, maybe name it like lab number 4, right? And run the code. So HW2 version 1. So maybe pedagogically it would be better to go over the code, but thinking of myself on your side, it will be a little boring to go through lines of codes without imagining what it does. So the dashed lines correspond to this meandric function that changes between 0 and 1, step functions, right? Yes? Okay. We need to explore it only in the range from 0 to 1, where x is a scaled 1 corresponding to L, right? And the field area corresponds to the area that will be like result of integration. So if we just integrate from 0 to 1 on x and hide change from 0 to, like, area of this little box will be 1/2, right? Which will be the term a naught, the expansion coefficient. Then this will be cosine with minimal frequency, frequency 1. The red line shows the cosine that we need. The dashed line shows functions that we fit, and the field area corresponds to integrals that we take. At the same time, when this figure is popping up, it shows like 1 is the frequency, spatial frequency of this cosine, and second number is the result, is the Fourier coefficient, which will be 0, right? You see that positive and negative parts are equal and they compensate each other while integration. Now I click any key once again. So here we have next cosine of the double frequency. So as we go from 0 to 1, it makes 2 full oscillations, and we integrate only from 0 to 1/2. And this it looks like a little Viking helmet or a little bird. So wings up by their area positive are equal to this little tongue down. They compensate, and it will be again 0. It may show minus, or maybe it's numerical 0. It can be like 0, 0, 0, 0, 0, and then something, but it's 0 with numerical precision. Clicking once again. Now we have a cosine of the triple frequency, and still it changes amount of the swings forth and back, but you see that upper and lower parts are equal in the frequency, and they give 0. Quadruple 5 times. Wait. And number 6, and they all are 0. So coefficients A naught is 1/2, and all other coefficients in front of cosine A sub k are zeros, right? So we do not need them. Continuing further. So here is coefficient B1. So we have a sign of the minimal frequency. We do have only an element of sign enclosed in this dashes that is completely positive. The area that we need to integrate is positive, and we know from your future presentations how to run numerical integration, right? So we see it is like 0.3 something. So it's non-zero. The index is odd. The value of integral is non-zero. Keeping going. If it is even, there are up and down elements. They compensate each other, and it is numerically as good as zero. Keeping going. If it is triple sign, then amount of this wings up and wings down are offset, and they are not equal. Two of them compensate each other, and one does not. And it is small but non-zero, 0.1. Keeping going. So expansion coefficient 4 is as good as 0. They compensate each other. Number 5 is again a little larger, non-zero, and 6 is again close to 0. Now I prepared to watch something different. So there were like 13 figures on the same pattern numbers. Now I click space. It did miss one important figure. But I'll skip it. So next thing that we are going to draw, and very soon we will go through the lines of the code. We are literally practicing the top line in this slide. So we are adding together element 0, and then this bn or b sub k coefficient and sign with different frequencies. But we are performing summation one at a time. So here we offset everything by 0.1 for a naught coefficient, and then the next non-zero term in this expansion is just sign of the minimal frequency. And you see it reproduces this up and down steps. Yes?
Yes.
Okay, thank you. If we click, we go, once we do change nothing, because when we go to element b sub 2, it doesn't change anything. When we add the third harmonic, you see it corrects where we had a top, like peak at the top of this plateau. Now with the third harmonic, it dumps it a little bit down. Where was a too much negative in this 0 area, the third harmonic pushes it up, right? So clicking once again, nothing, and once again, it is further increase of precision. So please try to verbally explain.
This is occurring.
Huh? What can you tell what do you see on your screen? In lay language. Whatever has is the best. I'll stop by and make sure. You're in the second code.
Mine's in the bed. Mine's the best.
Yours is the best. Can you interpret the figure that you see and just
Mathematically?
Yeah. Not in terminology, but there are two lines, one dashed and another solid red.
Yeah.
How they what are the differences and similarities?
The differences. I mean, they're both vaguely making the same shape, but the red is more wavy.
Yes, it is what I want to hear.
Oh, yes.
Did you, Elsa, you need to run different codes. Close this window, type Control C in command window.
Yeah.
And you're ready.
You copy this.
H
Did you paste it in here?
W.
And then I'm literally
underscore
tapping enter.
3E, and you need.
Yeah, it's gonna keep going.
Okay.
Oh.
Yeah. Yeah.
Fred, you're good.
Oh. And then, yeah. And it just keeps happening. Is it done?
That's good.
Yeah.
Well, mine is
I just
different
typed
than
in.
hers.
I
So
did-
You keep pushing space.
Going?
Yeah,
Yes.
that's now Melody.
Okay, now, Melody, can you, I'm not sure if I can focus camera on your screen, but can you explain what you see?
It looks like a sine wave, but it's got the little bumps at the peaks of the wave.
Okay, so, what is the similarity and difference of the blue dashes and red, solid red?
They both go like up and down between 1 and 0, but the red has the little like squigglies at the peaks.
Okay. Our dashes was the goal to fit, and our red is approximate representation. Can we say that the larger the number of the terms in the expansion, the better is reproduction of the dashes by solids?
So I think like the more little bumps we have in the red, the closer of an approximation we get to the blue.
Excellent. Very good. Very good. Okay, let's. A little interview.
I don't know. I have
Just
the
what
same
you see
results
how
as
you-
Ava.
What you see and how you interpret it. Let's make a little.
I don't know. I guess
Similarities and differences of solid red and blue dashes.
well, the red one resembles more of a sine wave, but I don't know. It doesn't look like a sine wave at the same time because it follows the same like rectangular pattern, sort of.
Excellent, excellent. Yes, yeah, thank you. You all are getting through things that I wanted to tell to you, but you're expressing it much better than I could. Elsa, continue your opinion. So similarities and differences of dashes and solids in this figure.
Well, would the dash ones be like a meandric function, and then the red one would be more of like a sine function?
Summation of several sine functions, right?
Yes.
How many? About 6, right?
Yeah.
Okay. What if we add more than 6, like 8, 10, 12? Would the coincidence between red and blue will improve?
Will it what improve?
Coincidence between red and blue lines.
I have no idea. Yes.
Okay, yo, thank you. Excellent. So, what was the goal of this exercise? Not in MATLAB, but when we did it in class, or not in class, when we did in a homework. What is the goal of this little problem? Why, like mathematically, or how the problem number 1 that Friend and Eva have in front of them? How does it formulate? To your memory, what you're reading.
Oh goodness.
Just try. You're not graded for this answer.
So like how question 1 lines up with what we did here?
Yes, exactly.
I mean, it has to do with like both cosines and sines, I guess, and it has both cosine, like the
But,
sine and cosine waves.
Everything is correct, but there is a volunteer to compliment.
Okay, so number 1, isn't this is like the ideal, and we are plotting something close to that, and we're trying to, we have an approximation of this and we're trying to get close to it.
Okay,
Is that right?
Yes.
Hold on. So is the blue dashed lines more of like the approximation of the actual function, and then the red one is the actual function?
Opposite.
Opposite?
Blue dashes are functions that we set as a task, and solid red is our answer.
Oh, okay.
Red, say yes.
Yes.
You agree?
Yes, I do.
Okay, thank you. Oh yeah, here. I can get a little of glory of, because when I was interviewing you, I was a headless. It was just so oh yeah, this is better. So let me try to summarize what you guys already expressed. The blue line was a task, and the red line was an attempt to reproduce this target function by some mathematical tricks, right? And there is a theorem. Since we are not in the math, we are not expressing or proving theorems, but any good function can be expressed as a series, as a summation of basis functions with certain coefficients, right? So we are adding together sines and cosines, and we are reproducing this step function, right? And basically any function, any periodic function can be reproduced in the same way, just the expansion coefficients will be different. Yep. Okay, now let's go through this lines of the code. And I believe we are performing really well because we spent half an hour for figures, and now we will spend half an hour for text. And then for a second hour, we also spend half an hour for figures, half an hour for text, and we'll be done. You can on your own make screenshots of the figures that you like and put in a PowerPoint. So if I go to the HW2_1, so anything after percent is how to say, anything after percent sign is not recognized by MATLAB, it's only a command. So periodic box. But you can please stop me. I will try to do the same, but you can express in your own words. And if I'm telling something unacceptable or incomprehensible, stop me. What? Correct. No. See, from 0 to 1, we have something unique. As we go from 1 to 2 or from 2 to 3, we have a repeating pattern, like same as 2 pi. And anything within unrepeatable part of the periodic function can be called periodic box. Unrepeatable part of the periodic function. Of the periodic function. Okay. Spatial shell increment. Next one is likely range of integration. Range of integration. Yes. I have no idea what are lines 6 and 7. So you can try your best. Maybe it is not used. Maybe if we remove the lines, program will not suffer. Okay. So when I set up k equals 0, probably we are looking for coefficient a naught. And then we express it as integration of the main function. Okay. Now I see z1 is our main function. I will change, like maybe add additional line. So z1 is the function to fit. Like if there are points, typically people fit them by linear function, but here it is very not a straight line. It is something strange. Therefore, we cannot fit it by linear function. And now I know what is here. So it is a sine of different frequency and taken. I cannot pronounce it. You will be laughing at me. I did a task for me that I cannot fulfill. Sine of sine. So plus or minus of the oscillating function. Teach me. Sine of sine. Yeah, it was like German accent. But I will listen to the recording as in language class and try to repeat.
It said the same. It's sine.
Sign of the sine.
Same.
Yeah.
So they are.
You don't pronounce the T.
I'm sorry.
Okay, then how do we do that? Sine and show plus minus. Sine of the sine.
The video boxes are covering up some of the stuff. Can we like put it in the corner or higher up in the corner?
This way?
No, like move the little boxes off the screen then.
Oh, okay. Better?
Yeah.
Okay.
That say try your best.
I already, well, I remember myself. So by playing sine of the sine, we get the step function. And you see, it is a little unusual to set up. I will waste time a little, but sometimes useless stuff. You are science majors. You are doing chemistry. And it is okay task to do, but you do not see immediate connection to chemical reactions and things like that. There are disciplines, STEM disciplines, where people would recognize, jump and say, oh, yes, it is what I do every day. So if you would be electrical engineering or radio electronics majors who design like headphones, audio systems for rock concert, then sound, which is a compression of like density of air, is stored as electrical signals. And there are analogous sound recording and digital. Analogous when you have vinyl disc, or when you record the needle scratches is deeper or higher, and then when you listen, the second needle just goes up and down, amplifies it, and then we hear the sound. And if the deeper sound has sparser dips, the higher sound has more frequent. But the quality of analogous recording is believed to be insufficient, right? Because one records the amplitude at each point. If one decompose a sound onto two tones, two musical tones, like on a piano, and just tells, at this time, we have this and this note with this and this amplitude. Basically, we reproduce, you play a musical instrument, right? Any sound at a given interval of time is reproduced as musical chord, right? Several frequencies playing at the same time with different like when you play a chord on like a keyboard or on a guitar, typically you do with the same strength, right? And now suppose that some of your fingers are strong like iron and another are fluffy, and you do some stronger and some lighter, or you have an orchestra telling like, you guys strong, you are just weak sound. And then by doing this, one can reproduce any sound. The Fourier transform does the same thing. It reproduces any function as a superposition of oscillator. Yes?
Transform the other day, and I saw it had a little comparison between a Fourier transform and a smoothie. So basically, the Fourier transform picks out all the different ingredients of the smoothie and what proportions.
It's very deep philosophical thought. I'm impressed. Okay. Yes, it's good analogy, but it is like general. And this equalizer modification of your sound is exactly what we do here. We amplify certain frequencies or quench certain frequencies. Does it click? You all digital. Okay. Whew. And if you would be electrical engineering, it was what you would be doing from freshman year. Okay. So this is some plotting, boring. Coefficient A naught, integration of the main function. Z1 is the main, type here, main function to fit. Main. I think I will do as much as I can, but I will stop literally at 6 to give time to other things. And you will see the pattern and continue as you can. And I think 20 minutes will be sufficient. So pause is when computer waits for us to hit any key. So here we have a cycle over different frequencies. When C is frequencies. So a sine of frequency 1. Now here we do multiply main function by cosine and integrate. So for integrating, we do summation, as some of you will be presenting soon. So multiplication of functions, and dx to make it correct answer, right? Hold off is erase old graphical information. Plot main function. Oh, function and fun have some similarities. Hold on means to keep the image main function and hold. And hold. Bar. What is bar? Oh, okay. It is. I think it is hidden somewhere. Bar. Oh no. I remember. Plot the field area. Would you agree? So we take this function times our cosine, and instead of plotting, which gives a line, we do a bar, which just shows a lot of these sticks, and then it shows like an area. And we fix the ranges of all of variables, because otherwise it will be jumping, like it will if range will be dynamically changing, then some people can get nausea. Okay. What is K frequency, A of K, expansion coefficient. Pose, wait for human or a human. Any human can come and hit the button. Okay, and now we are done for cosine part of Fourier transform coefficients. Now we do again cycle until 6, and if you want higher precision, we can do more, but then it will be incomparable with human abilities. Like if you do more, then computer will be a little more productive. You probably already got tired for doing this integrals by hand. Start cycle over for sinusoidal components. Oh, to make them different, instead of sine of the sine, I can do sine of the sinusoidal. So sinusoidal of frequency k. An expansion coefficient bk as an integral. Again, we have this sinusoidal function, main function, and then we integrate. Hold off, erase old figure, erase old graph, plot what? Plot main function. What main function as dashes. So this minus means it will be dashes, and hold. Then plot bar means plot the field area. Field area. Since Z1 main function is 0 after in the second half of the periodic box, the field area is limited, right? Okay, fix axis, fix axis. A equals frequency of sinusoidal, B A expansion coefficient. Pose, wait for human. Wait for human again, and do copy paste. Now start building solid red function, the function that we construct. Solid red function. At this point, we placed only zeroth term, so it is how to say baseline, right? Okay, now before we did cycle from 1 to 6 to find coefficients, right? Now we are constructing function out of coefficients. So cycle construct function out of coefficients. Again, set up cosine, cosinusoidal of frequency k, set up sinusoidal of frequency k. And here we are practicing our main equation of Fourier transform. Main equation of Fourier transform. So the target function is what it was before the cycle of summation, current version of expansion coefficients times current cosinusoidal, current version of sinusoidal expansion coefficient, current version of sinusoidal. It's too much to type. Previous, less precise. Is correct, previous W is corrected by an increment of the order k to make it more precise. Erase graph. What? Blue dashes as main. What? Red solid as result of fitting, as a result of fitting. Fix axis. Fix. Wait for a human. Task is on. Let me bring. Yeah, you saw this little snake coil. Let's have a quick look on the task. So find projection of a Gaussian wave packet, which is not an eigenfunction of H, onto plane wave. So the C sub k has similarity. There is a way to make notes. There is a similarity of the C sub k and this AKBK, right? So before we were practicing expansion in terms of sinusoidal and cosinusoidal. Here we do expansion in terms of imaginary exponential, but basically it is the same, right? Well, very similar. So we have the target function. Before it was a step function. Now we have a Gaussian, and we multiply it by the plane wave of a certain frequency k, integrate and get a coefficient. And later on, there is a inverse Fourier transform where we can reproduce. So this was our target function of x. we can reproduce this f of x as an inverse Fourier transform. So integrating dk instead of dx, c sub k, and then exponential with just different sign plus I plus ikx. And if things are done correctly, then first we find coefficients, store them somewhere, then practice this inverse transform, and we should get the same function or approximately the same function. And the level of approximation works that you have something that approximately reproduce our target function but has some error. And this error decreases if you have enough large amount of the basis functions. If they're insufficient, you have some wiggings. Make sense? Okay. So starting the code, the little element here is Gaussian exponential times a spiral of a certain wavelength. Therefore, as we go apart from 0, it dumps to 0 because Gaussian function dumps to 0. In the middle, it behaves like a spiral, right? Make sense? So it is a like multiplication of a spiral that we studied last week and the Gaussian function. If I click like pause, press any key, it will show another spiral, and it will show two numbers. So there is a little difference between Fourier and some people call what we do right now Laplace transform, but you don't need to remember names. In Fourier transform, the frequencies are discrete, the integer numbers. In this Laplace transform, the frequencies or wavelengths of the plane waves will be continuous. We will be changing them by a little. So the first number will be value of k, so to say frequency of the wave, and second number will be expansion coefficient. If you get back to here, it will be this c k and c sub k. Make sense? Okay. And as I push space, it shows starting from negative, then here it is a little bit closer, increases, and the c sub k changes. So as I keep pushing enter, the first number ramping up bigger, second number changes, probably increases. And in this little image, we see that frequency gets less and less. So the fringes get less and less dense. So when the frequency will get to 0, we are going to get absolutely the only real part, only Gaussian function. So look here, if I rotate, there is no imaginary or almost no imaginary part, and it looks like Gaussian function, right? So we multiply Gaussian function by the plane wave of 0 frequency, which is just a constant. E to the power 0 is 1. And if from now on I keep pushing enter, it will start increasing. So we considered plane waves with negative momentum going backwards. Now we'll go plane waves going forwards. So we see as imaginary component develops and density of fringes increases, and we go not too far until 3. Now, what is this little hump, hill?
Mine goes to here and then it won't let me input and it won't let me hit enter.
Controls.
Go backwards? That's not
Oh.
what I wanted to do.
Ah, interesting. No, backwards will not work.
Okay.
So let's just close it completely. Type clear. And start over.
Oh, you gotta do 3. I didn't save it with the E.
Okay. So
Oh, so
w-
now you
w-
just
wait
do
until
the-
it will go to the 3 and then wait a little. The
Now you've done it.
MATLAB stop. Okay, probably it probably it wants to rerun.
Let's go if it works. Okay. Oh, it makes so much sense. Please tell me all my things. Yeah. You typed in the code? What? You typed in that. Okay. Like my comments. Oh. Oh, so wait until it says +3? Oh, yeah, wait until it says +3. Right, it's gonna be here when you're hitting enter and all of your answers are coming up. Wait until it says +3 and then yeah. You're right. I got mine.
Oh.
No.
Okay, now it's like a yes.
Forget everything. I have this here just on both sides. I'm like, that's what I look like.
So what do we see and how do you interpret it?
Oh, we see like a Gaussian curve, but it's with blue columns, skinny blue columns, like a Riemann sum.
Okay,
Like to find the integral, you take the area of a function.
Of a bunch of rectangles, and so it'll be a decent estimate, but not like the perfect total area because you're missing like the
Okay.
little bits that are on top.
okay, good. Any more comments, any of you?
No comment.
Come on, you do.
Well, I still have to try and get my.
I'm a
So-
politician. I have no comments.
So, what is the connection between what you have on your screen and expansion coefficients for value of momentum from -0 to from -3 to +3? What is on, okay, a question. What is on x-axis and what is on y-axis for this little histogram? Oh, yes, you can criticize the author of the code legally that there are no labels, which is unacceptable. But please guess, what is x? How would you label x-axis and y-axis?
These ones are the X's, and these ones are the Y's. I haven't figured out what the name label is, but I know which one these are.
So if you do have a task of your homework number 2, can I touch it?
Yes, yeah.
Okay, and you
It's
look.
not mine.
Oh, okay.
It is from theirs.
Oh, sorry. So if we look into here, like,
And what we think
w-
X is.
yes, what is x and what is y? Just say something not necessarily correct.
Is it like equal to the -x²/6? Or is it the entire inside function is x? The entire inside function is x and y is c?
Wait.
Yeah, all this correct. All this correct. And the C is, well, I
Sort of correct.
no, you're absolutely correct. I just, camera is taking me. Oh, camera is taking me. And it just sounds a little strange. Y is C, but the meaning of y-axis is the C coefficient.
Yes.
Okay, thank you.
Okay, well,
Too much? Tired of me? Tired of physical chemistry? Did you hear what else I taught all of us?
yes.
Yeah, I don't want my head to be trimmed. Okay, invisible man. So y-axis is C sub k. What is x-axis?
Isn't it just?
I didn't hear it. Try once again. Yeah. No, so C sub k means value of coefficient C is different for different values of k. What is x-axis in this graph? Yes, you all did great. Yes. Okay. So what did you get in your answer when you completed your homework too?
Sigma pi times e to the negative sigma k squared over 4.
Okay, so what you have plotted as a histogram is exactly this equation. So e to the power minus k squared, right? When k equals 0, this expansion coefficient is maximal. C sub k is maximal. When k is either negative or positive, it declines, right? So we basically reproduced your homework effort with programming.
That was so much faster. No, this is way better.
Oh, okay. All agree.
Yes.
Okay. So it is C sub k. We performed this integration and we got C sub k. And homework 1 would be finished at this point. Homework 2. But let's just practice a little bit of curiosity and see if we can reconstruct our. So right, let me tell a little bit more. Our original function is expressed in space of position. I know there is a little ambiguity. So space of position, space in abstract sense and position like our position in the real world, X. Now, when we do this Fourier transform, we are expressing the same function in space of momentum, in space of frequencies of this plane waves. So it just converts our function into different world. It is analogous to how we make digital sound recording. We record our complicated profile sound wave as a summation of several basic tones, right? All agree? Okay. Now we do C sub k is the same function in momentum space or space of ideal tones. Now, can we reconstruct from momentum space back to the position space? Can we practice, let me select it, this thing that I'm going to highlight with cyan color? Can we take the C sub k, multiply it by plane wave and reconstruct f of x? Same as we did before to reconstruct this step function by sines and cosines. Can we reproduce our Gaussian function by adding together C sub k with this oscillating coils? Okay, let's get back to the MATLAB code and slowly push enter once again. So right now we show solid black is our ideal Gaussian function, and dashed red, sorry for changing meaning of the function from task to task, is our little contribution from the very first C sub k of -3. So you see it makes like 3 humps, but its contribution is quite small. Now I hit enter once again, and it adds another frequency and it increases. By now, contributions of all of these 3 peaks are approximately the same. But in order to reproduce function, we need the one in the center to be taller, the ones and the size be lower. So I keep entering. By now, it just increases. But as we overthrown over 0 and we start adding together different, and you see, when we are below 0, we reproduce this Gaussian real function as this coil, right? There is a little button. You see this blue thing rotate. Yeah. Oh. If Elsa, if you try arrows up, down, just arrows on the keyboard. Because I didn't wait until the end. I do it in the middle. Yes. And it is what I want to say. When we add together C sub k only for negative case, then it will have this representation is very poor and it has both real and imaginary parts. If I keep performing this summation, so into positive, then the imaginary part will become smaller and real contribution in the center will become bigger. So going, you see imaginary getting smaller, real, especially in the center, become bigger, keeping going, checking. So it has less and less imaginary, more and more in the center, going. And when I approach, it will be not ideal, but closer. So now we see the real is maximum and imaginary is 10 to the minus 16. Yes, so it is numerically 0. So we get numerically, we reproduced real function. But it is not an ideal fit because we didn't include enough values of momentum. If we would make this code a little longer and start maybe from not from -3 to 3, but from -10 to 10, the way how the function is reproduced will be much better. I'm going to make a little tour and see how you're doing on your screens, and then we'll go over analyzing the text of the code.
Well, I didn't have like yeah, I have to buy this computer because I was having trouble finding a computer repair technician. Oh.
Whew.
I still haven't sent it in and I still have to deal with this. Yeah, I'm kidding. Sounds like it.
Works just fine. Dimitri, I'm sorry, mine shit itself right before you were gonna come and see us. But I will get it back.
Things happen.
Oh.
But I saw it. I do not doubt. So instead of pushing enter and then patiently waiting, you're just like keeping it pushed
Yeah,
pedal to the metal.
yeah.
Okay, I understand it. Okay, yeah, I think all works perfectly. What to the wall? I will listen to the recording.
Words in Russian and we will teach you stupid American sayings that don't make any sense.
Yes, I need it. I need it so badly. Just to you want to say, or you want just high five?
Okay. Thanks, Blake.
I feel I do not know what it is, but I feel by your smile that it is a provocation. Just in case. Okay. It's a goal.
Okay. That was like you and Maria, that's right.
Okay, so if you wanted, you may have made your screenshots to the PowerPoint, and now we are going to the text. So the so X is size of the. So there is no there is no periodic box, just size of the active space. Increment spatial Oh, I have a great idea, after which we may not be friends anymore. It's quite boring for me to type something when you're having fun there. Let's just call one by one and type here on this computer. Huh? But no, take turns. While Melody is typing there, I will type on her computer. Yes.
This I can be a part of.
Okay.
Let me get caught up.
Okay, so what is sigma? I think sigma is another word you taught me. Width.
Oh, well, yeah.
That's it?
Yeah. Well, but you don't need to follow me literally, express as you see it. Phi not equals exponential. So it is our main target function. Function of what? In space of position, right? In space of position. I feel a little uncomfortable because space and position are kind of mean the same, but okay. F equals 0 size X. Zeros means it is an empty array of the same size as the main function. What is K max? Oh, okay. I need to quickly get back to the line 3, size of the active space for position. For position on. And now I go back to the line 9. Yes, thank you, Melody. And then type the same size of the active space for momentum. 10 number of grid points. Number of grid points. So what's the total number of 43? Okay, I think it is enough. It's time to rotate.
My turn?
Yep.
Okay.
All right, let's rotate.
Am I going to help you?
Wait, what?
Oh, I wasn't intent. I thought I will rotate only with one who goes there, but you can keep rotating. It will be true collective effort. It's an interesting game.
I just saw like I just saw a bunch of people stand up.
Okay, so line 11. So before doing line 11, I need to return to line 4 in a special increment or infinitesimal increment in this space of position.
This is on line 4.
Means small. No, an additional. And then I return to,
Infinitesimal?
yeah. Like when we have dx, it means infinitesimal
Okay,
increment.
so infinite,
There it is.
simal. SIMAL.
Oh, S-I-M-A-L. Oh, that's how I had
There
it.
you go.
Okay. Increment. Infinitesimal increment in the space of position. Okay, and now there is an analogy between the line 4 and line 11. And in the line 11, we have infinitesimal increment in the space of momentum.
Yeah.
Well, since you increased, you made one line more, now on your screen it will be line 12. Decay equals K max divided by, sorry. Line 12. It's not the accent, I just hard to pronounce. Decay equals K max divided by grids. So it is the same meaning as in line 4. Infinitesimal increment in the space of momentum. Make sense? So we are working in two spaces. Our regular space.
Infinitesimal.
It's not physical chemistry, it's math. Yeah, copy paste, much smarter.
I know.
And now
In the space of momentum.
replace the very last word, position, to momentum. Okay. What is I equals 1? I don't know. Okay, let's. It is a counter. Counter, not like a kitchen counter, but the variable that will count something.
Right.
Counter that will get an increment.
Is that
That's your
like when you have the sigma, it's you have to put I equals 1 or I equals 0 at the bottom? It's like where you start at?
Oh, yeah, so like when you have the summation, like the big sigma, is that the what you write underneath the sigma? or is it-
No, it will be K.
Okay.
Oh, okay.
It will be K. Oh, now line 13. Now we are opening a cycle, open a cycle over.
I don't know why I'm looking at the board.
Would you repeat, Melody and Elza? Would you repeat what you've just told? I like it and I cannot do better. Just repeat your, scroll back and repeat your last sentence.
Oh, the uppercase sigma, like when you do a summation.
Okay, maybe not upper, but under case. No.
What line is this for? 13?
13 if I didn't change the number of lines.
So the I equals 1? Oh,
No, yeah, you're typing in the right space. How you would you?
I understand. So this is like how many points we have that are gonna be contributing to the summation.
Yes.
So n is equal to all of the different points together, right?
Eva, may I ask you for a favor? Thank you. By
is it like this? Like you have this, it's this? That is what it is?
summation subscript.
The
Yeah.
starting
I
point.
don't-
Summation starting point of the summation subscript. I will type it, but as a favor, would you please type Alt tab to bring up the PowerPoint with this blue highlight, or just click on it? Yeah. So this the integral in the blue thing, right?
Yes.
Goes from minus. The values of k goes from minus grid to plus grid.
Oh, okay.
And if we count on the expression that is to the right, c sub k equals blah, 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 the k takes values from
Okay.
minus grid to plus grid.
So we open a cycle under bounds.
It's
Negative
the
grid
bounds
to
of
grid.
the integral?
Under bounds of integral. Type on your own. So index.
Like this?
And we do not need to have all the same, if there is a,
From negative grids to grids. Under bounds from negative grids to grids.
okay. Yeah, I like it. And also, what did you type? What did you type for this line 13?
I said open cycle under bounds of an integral. So like
Okay.
when you have the integral, you have like negative whatever to
Okay.
whatever.
And Fred?
Just pretty much the same.
Okay, and I did type, and maybe you guys are more correct than I am. I type open a cycle over index of a point in the momentum space. Okay, so we understand each other. So next line, the grids were discrete. So maybe let me just open a cycle over discrete. DISCRETE.
Just kidding.
Okay, and now the line under this. So what is opposite to discrete? Continuous, right? A continuous value of momentum. Good. I'm proud of myself. Whew. Line 16.
That's already just a-
Imaginary unit, right? Square root of -1 will be I. And when I was typing this code, I didn't know that MATLAB understands just letter I. I thought okay. Then line 17 is plane, or 18 is a plane wave, right?
That's what we're supposed to remember when we wake up in the middle.
Exactly. So next one.
I'm gonna dream about plane waves.
So AA equals phi k times phi naught. So this, and what is phi naught is main target function, right? So now it is a product. Oh, by the way, plane wave of a frequency A. And now line 18 will be a product. Do I need an article A in front? A product, the product,
Yeah,
or
it
just,
doesn't matter.
okay. Thank you. I feel much
It's
comfortable.
just notes.
In my native language, there are no articles at all. And if I want, one is learning English, just randomly put like A, the, who
Yeah.
cares?
Like as native English speakers, we probably do the same thing.
So a product of main target function and a plane wave. Whew, good. Are you tired?
It's switch out time.
What?
for-
Let's
Fred, can you-
switch.
You're gonna have to use the mouse if you wanna,
Oh, thank you.
yeah, the touchpad doesn't work. All right.
Alright, you got it, Fred. You got a high five.
Oh, yeah,
Yes.
that was so good, Fred.
Take two to high five.
Thanks, thank you.
Not all the
So
time.
Guess everyone watches and. Yeah.
oh, okay.
Your friendly
But my
FBI.
friend, camera on your laptop probably doesn't work.
No, it's so I don't accidentally join into a Zoom call with like the camera on. If I'm just like rolling out of bed.
Yeah,
Yeah.
Okay.
yeah, that's why.
Next line. So here we plot a, well, it's not a spiral, it is a, limited spiral. Well, we just plot this function, which is what? A spiral in the center that fading out as we depart from the center. Then, and here what Fred taught me to do, use the mouse. Fix the axis. If I do not do it, it will be like changing scale and some people get dizzy. Now, line 22, and for Fred it will be 23. So C sub K of I. Yeah, what is it? How? Okay, I kind of reconstruct my thinking from. So first, it is just practicing the integral, right? So finding the expansion coefficient corresponding to momentum K. Integral. Try your own. Everyone.
Can you say what you said again?
I don't remember. I'll try to think over, and so it is an integral corresponding to an expansion coefficient
Expansion coefficient.
corresponding to momentum K. Corresponding to the momentum value K or frequency K. Okay.
Good, Fred.
Okay. Now I'm adding another line because there is this mysterious when I wrote it a few years ago and now I'm looking as a baby on it. So why we use this another counter index I? Because if we want an index of an array, it must be integer, natural. It cannot be negative. And here we are counting for negative values of momentum. And we need to match unmatchable. So we need to use integer number to count negative things. Therefore, you use this integer counter. So maybe, yes, in line 12, in front of counter, I put integer counter. In integer kitchen counter. Okay. And this expansion coefficient is stored to array element number I. Stored to the array element number I. Okay. Now in the next line, no, next line, where I don't know how, when I was typing it, I was not meaning to pronounce it. KKI equals K. Right?
Yeah.
Okay. So the value of continuous momentum, which can be negative, the value of continuous momentum is stored in array element number I. The value of continuous momentum is stored in the element of array k number I. Okay. Pause. Just wait for human. Wait for human. Then if we just list some variables without any comment, it means just print them on the screen. So print the values of the momentum and expansion coefficient to the screen. Okay, and now next line, I equals I plus 1. To form here form an increment of the counter of the discrete counter of the discrete counter variable by 1. Just go to the next element of array. Okay, and then and cycle, and the cycle over. So what? How do we call it? What was the cycle over? Over values of momentum. Over values of momentum. Okay. The next one, bar AK, real CK, hold on. So why there are 2 of them? Oh, because who knows whether it will be real or imaginary. So we show both. So plot both real and imaginary parts of the Fourier transform of the main function. Adding next line and making a comment. This is a visual representation of the answer to the homework 2, problem 3. X-axis is the value of momentum. Y, we discussed all of this. Y axis is the value of expansion engine coefficient. Remember equalizer in Unix.
It's CFK.
Yep. Yeah. CFK. Pause. Wait for human. For a human. Fred, is it enough of your rotation?
I could go all night. It is almost done.
Yeah, let's
No.
do some with something further.
I'll take some.
Equalizer and music.
Music.
Music. Oh yes, I misspelled it. Fred will fix it.
Yeah.
You'll fix my errors. I type music as music.
I'll try really hard, but I can't type very fast.
Equalizer in music. Whew. Okay.
Yeah.
So hold off means erase old graph. I equals 1. So restart the discrete counter from the beginning.
From the beginning.
For grids to grids. So I'm making just a note, not for typing. It looks like we do have 3 different variables for the same thing, just looking from different angle. So we just need to count the value of momentum, right? And we have the discrete counter that goes from minus grids to grids. We have a continuous value of momentum, which is k, and we have the discrete counter that takes only natural values, right? So the I equals 1, it is discrete. It's not only discrete, it is natural. Means it's never negative. Natural counter from the beginning. Now the lowercase n goes from minus grids to grids. This is also counter, but it is integer. It can be negative. Discrete counter of points in momentum space that can take negative values. Okay.
Discrete counter of points.
Try your own. I'm not insisting.
Just come up with your own.
Points in momentum, though.
Points in momentum space.
They can take negative values.
Now, line 46 is a continuous values of momentum. Points in momentum space. Okay. Now, line 47, plane wave corresponding to momentum value k. Note, note the negative sign as we perform an inverse transformation. Inverse Laplace transformation. Okay. Oh, yeah, good. So next line, FF equals FF plus phi k times ck times dk. So we are accumulating our fitting function. So there is a function that we need to fit the Gaussian exponential in Cartesian space, and there is an approximate function. you understand? Or not sure? Elsa, may I ask you for a favor, for the same favor as Eva did to me? Would you please bring this blue PowerPoint with blue box?
Oh, what did you do?
You saw my whole life. You saw like all photos, chats.
It's
Uh-oh.
just far on the right.
But you can do Alt tab. By Alt tab, you can browse one by one through all applications. So in the blue box, in the blue box, we are reconstructing the target function in approximate way, right? And the variable ff that we are trying to describe, it is exactly this function. So we are trying to implement the blue box. And now try your creativity to express it. An attempt. Elsa, to go back, try Alt tab. Oh, you did it.
I can see it.
Okay, so an attempt. I'm just trying to type it correctly. An attempt to program the blue box. To program the blue box. Yeah. So what is the blue box? It is what? It is an approximate representation of the main function in the position space. Note that it is approximate. It's already told. Now we see this ff equals ff plus something. So we at each iteration we do what? We at each iteration we add a new plane wave we add a new plane wave of momentum A with weight coefficient taken from mass transform. The shorter the better. If it is long, I'm not happy with. I'm not proud of myself. The good explanation should be short. I can read what I typed, but try to do better, and I hope you did better. Attempt to program the blue box. It is an approximate representation of the main function in the position space. At each iteration, we add a new plane wave of momentum k with a weight coefficient taken from the Laplace transform.
I don't think I got the last one.
That's okay.
Well, yeah, he just said it, so you can get it.
Okay, Elsa, let's come back to the blue box. Well, let me read what you have. An attempt to program the blue box, approximating the representation of the main function in the position space. At each iteration, we add a new plane wave of momentum k. And this each new plane wave, which is phi k, is multiplied by coefficient c sub k of index I, which is just a weight, proportion, percentage at which the given plane wave contributes to the final function. Do not take it literally, just try your own words. What's ridiculous? Okay, play. Come on, it's simple. Okay, let's do simple. Plane wave with a certain proportion. Okay, everyone is supporting. Like,
Yeah.
I just proportion, weighting coefficient, percentage. Okay. Code of erase previous image. Plot 3. So phi naught. K1. So it is a plot main function as solid black line. So K means black, dash, single dash means solid.
Black. Lost letter.
But there's a
But
Yeah,
B
but B
also
is
can
blue.
be blue.
so L.
Al is for lime green.
I do not see the logic, but maybe if it would be, well, does C stands for a sign? Maybe K as a contrast, but it should be C. Okay, yeah.
Help. Oh.
Okay, hold on. Keep the previous image.
Whatever colors come up on my graphs on here, you're gonna stay like that.
Keep the previous image, like do not erase. So stack images on the top of each other. Plot 3 real FF, imaginary FF, dash, dash, view 2. Plot resulting approximate representation of the main function, right? So, and in brackets, blue box, dashed line. Okay. Pause, wait for human. For a human. And so you taught me. Mission has been accomplished.
Yes.
Okay, time to rotate. Yes. What? Uh-oh. It goes for recording.
They could see, they could see.
Okay, copyright Elsa. Oh, I can just stop sharing and then. So just what I believe I was sending an email, and it's very easy to fool me. I don't remember what I was typing in the email, but let me bring it up. So add a comment to each line of the attached code. Copy paste most important figures generated by both codes into PowerPoint file. By the end of the lab, submit by email 3 files. So your 2 files with commented codes and 1 PowerPoint with a couple of figures. You know how to do screenshots, right? You not, it's not possible to show everything, and it will be maybe too much of my time. Just when you are running, you can rerun the codes and screenshot most important figures that are worth of mentioning and describing. Like if there are a series of 30 similar figures, you you take only one, right? And then I look forward to getting your emails, and as soon as you're done, you feel free to